and welcome back to this series on intermediate statistics. And today we're going to be adding another classification method to our list of classification algorithms, and this method is going to be called support vector machines. So up to this point we have obviously a few classification methods such as decision trees, random forest, k-nearest neighbors, and logistic, amongst other types of regression. So we're just going to be adding this to our list because this method, SVMs for short, is very robust and adaptable to different types of data sets and structures. Also, if you do not get the exact results that you want, support vector machines can actually be adapted or modified slightly in order to give good results, depending on the results that our original SVM method was giving us. This is going to kind of come in parallel to what we did with multiple linear regression, where we introduced alternatives such as lasso, ridge, and other types, where pretty much all we're going to do is we're just going to modify the functional that we're minimizing or optimizing over in order to get the results that we want. And obviously we were able to change multiple linear regression into, say, polynomial and nonlinear regression via just transformations. And SVM has pretty much the same exact ability to adapt to whatever we want. Now, before we get into that, I need to quickly go over something from linear algebra that you may or may not have forgotten, and that's how to find the orthogonal distances from planes. Let me just draw a two-dimensional picture to give you some idea of what I'm talking about. So let's assume that we have two predictors, say x1 and x2, and let's assume that we have a linear plane, or in this sense a line, that has the equation 5 plus 3x1 minus 2x2 is equal to 0. You can write x2 as y and write it in terms of y equals mx plus b if it makes you feel any comfortable, but this presentation of this line is going to be what we're going to be working with, so I'm going to stay in this particular structure. Let's assume that we have another point in this space. Let's assume that this point is called, say, xk, where xk is equal to 7 minus 3. 7 for x1 and minus 3 for x2. And again, let's assume that we're interested in finding the perpendicular distance that this point is from that plane, right? And this plane we're eventually going to call h. Right? So we want to find the perpendicular distance hk is from h, and this distance we're actually going to give a name, so we might as well just give it the name now, and we're going to be calling this psi k. So psi k is going to be eventually the perpendicular distance from a point to that eventually hyperplane. So how do you find this distance, psi k? Well, using properties of projections, you should be able to find that the denominator of that projection is just going to be the norm of the coefficients in that particular structure. So in this case, this is going to be our beta 0, this is going to be our beta 1, and this is going to be our beta 2. And we're going to be grouping these two coefficients, beta 1 and beta 2, in a vector called beta, and the denominator is going to be just beta 2. And the numerator is just going to be this expression evaluated at our point. So that's going to be equal to 5 plus xk transpose beta, where beta does not contain our intercept term. So for us, that's going to be equal to the absolute value of 5 plus 3 times 7 minus 2 times minus 3, all over the square root of 3 squared plus negative 2 squared, and that's going to come out to approximately 8.875. All right, so therefore, if we have the general case as I mentioned above, so let's assume that we have our hyperplane, and our hyperplane h is generated by the equation beta 0 plus x times beta, and here x can be a matrix, and let's assume that that's set equal to 0 and beta is a p-dimensional vector, then the distance that a point xk is from that point is going to be equal to the absolute value of beta 0 plus xk transpose beta, all over the 2 norm of the beta coefficients, where that coefficient vector beta does not contain our intercept. Here, xk is going to range from 1 to n in terms of the subscript, So that's going to be equal to, say, xk1, xk2, all the way down to xkp. Obviously, if you want to do that transpose with that intercept, you can append a 1 in front of it. But of course, k is going to range from 1 to n, because that's going to be representing the points that we're eventually going to be classifying with this support vector machine. So now that we got our linear algebra review, underway, let's introduce the mechanisms that we're going to need for SVMs. So now let us talk about what it means for a data set to be linearly separable. What we're going to do is we're going to start with the assumption that our classifier y is binary. That is, we only have two classes, for example, success and failure. We're going to be defining one of those values as 1 and the other as -1. Right? That's going to set up your if-else statement if you're trying to code this. So y is said to be linearly separable if there exists a p-dimensional vector, beta, and a constant beta 0, such that if y is equal to +1, then beta 0 plus x transpose beta is greater than 0, and this should be greater, not greater than or equal to. And if yk is -1, then once you plug in that associated point into that particular hyperplane, you should get a negative number. If this definition doesn't make sense to you, let's draw a picture to illustrate it. So what we're going to do is we're going to have, let's assume two variables, say x1 and x2, and let's assume that we have two classifiers, -1 and +1. Let's draw our positive ones over here in circles, and let's draw our negative ones over here in x's. Your goal is to separate these two data sets by a line, or a plane, generally speaking. So our +1s are over here, our -1s are over here. So if you have the ability to draw a line, and that line doesn't cross any of those points, then we say that that data set is linearly separable. There's obviously infinitely many lines that you possibly could draw here, but what we're going to be doing is we're going to be searching for 3 planes that separate it in the following way. One of the restrictions that you are allowed to break is that these lines can touch one point. For example, notice that I'm touching that x with that line, and let's assume that we have another parallel line. Let's assume that those are those points. So if you can find these two planes, then you should also be able to find another plane that's in some sense the median hyperplane that is parallel to all of them. Right? So very important. What we're going to be doing is searching for these 3 hyperplanes for which I'm going to be calling h+1, h-1, and h0. Right? And again, we're allowed to have some of these points, for example, this point and this point for h+1, and this point for h-1, to touch that point, but you cannot have points in between these two hyperplanes, h1 and h-1. Right? So for the algebraic side of these planes, what we have here, h+1 is going to be the plane beta 0 plus x beta is equal to +1, and h-1 will be equal to beta 0 plus x beta is equal to -1. And then we have this third plane in the middle, h0, which is going to be beta 0 plus x beta is equal to 0. This plane is going to be what we're going to be using to classify new points, and hence we're going to be calling this plane, h0, the decision plane. One very important thing that you should be able to notice is the following. So if your data set is truly linearly separable, then there should exist at least one point in both of these classifier points, 1 and -1, we're going to call them xi and xj, such that beta 0 plus xk transpose is equal to 1. So this is going to be xk. So that is going to belong to h+1, and we should have at least one point that belongs to this plane, which is h-1. So in this picture, we have 2 points that belong to h+1 and 1 point that belongs to h-1. Right? So we're going to be trying to find what values of beta give us these planes, and we're going to specify some things that we're going to be optimizing over in just a moment. Right? So just a couple notes that you should notice here. h+1, h-1, and h0 are parallel hyperplanes. So if they are parallel hyperplanes, then they will have a fixed distance. in particular a fixed perpendicular distance. Fixed perpendicular distance from one another. And this is where that linear algebra I started today with is going to come into the picture. Right? So let's suppose that xi belongs to h, positive 1. That's going to be our support vector. And let's assume that xj belongs to the hyperplane h, negative 1. So that's going to be also a support vector, but on the other side. So what is going to be the perpendicular distance from h0 to xi? Well, that's going to be equal to, by our projections, beta 0 plus xi transpose times beta, all divided by the 2 norm of our beta coefficient. But keep in mind, beta 0 plus xi transpose beta is going to be equal to 1. So we're going to have the absolute value of 1 all over the norm of beta 2. And that's just going to be equal to 1 over the 2 norm of beta. And also the perpendicular distance from h0 to xj. Right, so let's just draw a picture of what we're doing here. So here is our h0 in the middle. And our xi is located here. So this distance right here is the distance from h0 to xi. And now we have this other point, xj. So xj is this distance here. And what we want to do is find this distance right here. So that's going to be equal to what? You can probably take a guess. So that's going to be equal to the absolute value of beta 0 plus xj transpose beta all over the 2 norm of beta. But that's just going to be equal to negative 1. So that's also going to be equal to 1 over the 2 norm of beta. So that's that distance right there. Right? So what we have here is if we were to just ignore the points overall, and let's just draw our support vector planes. So if this is our h1 and h minus 1 with our h0 there, then you should be able to find this maximum distance, this maximum perpendicular distance between these two planes. So what would that be? Well, that would just be the sum of these two other distances, 1 over beta 2 and 1 over beta 2. So we add them and you get 2 over beta 2. So therefore, the max perpendicular distance between the h plus 1 hyperplane and the h minus 1 hyperplane will just be equal to 2 all over the 2 norm of beta. Okay? So that's what we're going to have for these two hyperplanes, which, keep in mind, hopefully should be separating our data. So what is some of the characteristics that you probably want about this distance? Do you want this distance small, or do you want this distance close? Take a moment and think about it. So what do you think? So technically speaking, we would like these planes, h plus 1 and h minus 1, to be as far from one another as possible. If you kind of think about it this way, if you have a bunch of circles here and a bunch of x's here, and they're really close to each other, there's not much significant difference between them. So the distance between those two hyperplanes is going to be super, super small. Whereas if you have these zeros here and these x's here, obviously they're very different from each other from a predictor perspective. Therefore, since these planes are significantly large, or that distance is significantly large, therefore the classification between circles and x's should be more substantial. Right? So pretty much what we have here is, okay, we know how to calculate the distance between these hyperplanes. We can always, randomly pick hyperplanes and find the distance between them. The only difference so far, or the only issue, is we don't know how to find those betas yet. But nonetheless, what we have here is we want to maximize this distance, this perpendicular distance, between those two hyperplanes. And in particular, we want to maximize 2 divided by the norm of beta 2. Right, so that's one perspective, or we can minimize its reciprocal. That is, we can minimize the reciprocal of 1 over delta plus max, which is going to be equal to 1/2 beta 2. And this minimization problem should look very, very familiar from a least absolute difference perspective, which is one of the alternatives to least squares regression. And obviously, one of the issues with this particular method is that it's not exactly solvable in a nice way. So usually what we would like is to turn this minimization problem into a quadratic convex problem and instead minimize 1/2 the square of that norm, which technically speaking is going to be 1/2 times beta 1 squared plus beta 2 squared all the way down to beta p squared, right? So once you have that, then we can find those particular planes. And why are we guaranteed that this minimization problem even has a solution? Well, this is a convex optimization problem, and since it's a convex optimization problem, it's going to have a unique minimum because it's of the quadratic variety. So what we have here now is a constrained optimization problem. So our goal for constrained optimization, because we have to do it for all points from k is equal to 1 to n. So what we're going to do is we're going to minimize 1/2 beta 2 squared subject to the constraints that yk times beta 0 plus xk transpose beta will be greater than or equal to 1, right? And keep in mind, this is under the assumption that the data set is linearly separable, and this is going to range from k is equal to 1, 2, down to m. So we have n constraints and one objective function that we seek to minimize. And since this is a minimum or a quadratic variety problem, has a unique min, therefore once we solve it, we're able to get our beta 0 and our beta coefficients, where beta ranges from 1 to p. And then everyone's happy. All right? So once we have our beta 0 and beta 1 through p, using whatever optimization algorithms that you know so far, then the question is how to use a support vector machine. So let's assume that beta 0 comes out to 12 for our data set, and let's assume that our beta is equal to 5 minus 3 and 2 transpose. So we're going to be assuming that our data set is indeed linearly separable, else you in some sense won't be able to find these particular numbers. So again, our goal is to classify a particular point, and let's assume that x new is going to be equal to, notice this is x1, x2, x3, so I should be able to give you 3 points, 1, 5, and 8. Right? So our decision hyperplane is going to be equal to beta 0 plus x transpose times beta is equal to 0. So we just need to see, when we plug this point 1, 5, 8 into this particular plane, are we going to get a positive number for plus 1 or a negative number for minus 1? So this is going to give us the following. So h0 will be 12 plus 5 times 1 plus negative 3 times 5 plus 2 times 8. And this is going to give us 12 plus 5 minus 15 plus 16, which is going to come out to 18, which is a positive number. Therefore, what we're going to do is we're going to classify our new point, x new, as a plus 1. And this is because h, our decision plane of x new, turned out to be a positive number. Keep in mind, the more positive it is, the more confident we are with the classification. And, of course, what if we were to get a negative number for this output? So let's just briefly mention this. So if h0 x new turned out to be negative, then we would classify this particular point, x new, as a minus 1. And that's how you build a support vector machine in the possible and ideal case that our data is linearly separable. But what if it's not? One of the easier solutions in the case where your data set is not linearly separable is to consider polynomial or nonlinear terms. But keep in mind, this is subject to a couple issues. For example, let's assume that you have that data set here, and let's assume that we have this data set here. You should be able to argue to yourself that this data set is not linearly separable. Now, if this data set is truly to be separable, then it might be the case that this data set is lying on some sort of non-two-dimensional geometry that doesn't really represent this best with planes. And we have solutions a little bit later on how to deal with that. But in this particular case, a hyperplane is not going to be able to separate these data sets easily. So you might be like, okay, well, I can obviously fit a nonlinear plane. I guess it's not really a plane at all. For example, a quadratic plane or a quadratic surface. between these points, and now our data is separated. But keep in mind, this is prone to overfitting. So we're not going to consider that. So when you have a data set that is not linearly separable, what we're going to do instead is we're going to try and separate this the best we can with planes by intentionally misclassifying points. For example, let's assume that we have these points here and these points here. At this present point, notice that these points are indeed linearly separable. But let's suppose that we throw a couple x points here and a couple y points over there. Right? So in this case, it's mostly separable with the exception of a couple points. So what we're going to do is we're going to try to still fit two planes here, and there's our decision plane in the middle, while intentionally misclassifying points to start. So in this case, notice that this point here is going to be misclassified, that point is misclassified, and so is that point. Also notice that this point here, and this point here, and also that point there are misclassified too. So what do we want? Well, keep in mind on how to find perpendicular distances, we want these distances to be equal to 0. That is, these distances are with respect to the -1 hyperplane, if these are the -1s. And if these are the +1s, then these distances should obviously be equal to 0. Right? So here's what we're going to do. So if yk is equal to 1 and h plus 1 of xk is bigger than 1, or if yk equals -1 and h minus 1 xk is negative, then the perpendicular distance between that point and that associated plane will be equal to 0, because they're on the right side, or the correct side, of their associated hyperplane. Because keep in mind, yes, these other points do have perpendicular distances, but those distances aren't causing us any issues. Therefore, we're going to be associating these distances as 0, and we're going to be penalizing all distances for points that are on the wrong side of their associated support vector boundaries, which we call soft margins. So if you are on the right side of your boundary, we're not going to penalize your distance, psi k, but if you are on the wrong side, that is, if you are negative but you're supposed to be positive, or you're positive but you're supposed to be negative, then psi k will be equal to the absolute value. And keep in mind, let's assume that this point, yk, is equal to plus or minus 1. Then psi k will be equal to minus plus 1 plus beta 0, because keep in mind, if it's equal to 1, then you have to subtract 1 from both sides, and if it's equal to -1, you have to add 1 to both sides, so it's always the opposite sign, plus xk transpose times beta, all divided by the 2 norm. Right? So that's going to be that perpendicular distance that we're going to be penalizing. Right? So now that we have our strategy to build our quote-unquote soft margins, keep in mind, support vectors in our data set are not guaranteed to exist in this particular case. What will be our optimization problem? Right? Because if we can build an optimization problem, we can find those betas. So as usual, we want to minimize 1/2 of the square of the 2 norm, and then we want to penalize all of our distances. So we can do the sum from k is equal to n of the absolute value of psi k. Absolute value is not needed here because we are forcing our size to be all positive. Now, just like we did with ridge regression and lasso regression, sometimes we want to penalize these at faster speeds and have more control over how they are penalized. So we're going to introduce hypertuning parameters delta and p to control that. So let's mention our constraints. So again, yk times beta 0 plus xk transpose beta must be equal to greater than or equal to 1 minus that distance for which we are penalizing, so that this is always going to be a positive number, so we don't need any slack variables from the perspective of optimization. And k, as usual, is going to range from 1 to m, with psi k all positive. Right? So once we are able to solve this optimization problem with whatever optimization problems you know how to use, then of course you're going to have this beta 0 and this beta 1 term and this beta 2 term all the way down to beta p term. Once you have that, then you can classify as usual. Right? But keep in mind, our model is not designed to be perfect here because it's going to intentionally misclassify as few points as possible. They can, in some sense, make the best decision under the assumption that these data sets are, in some sense, linearly separable, but with a couple of variants or residuals or outliers that are potentially thrown out the classification process. So up to this point, we are able to solve at least two different types of classification problems for binary classifiers. The first case is when the data set is linearly separable. So you should be able to have this clean, pure classification process. And the second case is where, the separability is not exactly clear-cut, but you're still in some sense able to draw these two hyperplanes such that for the most part, the data set is separable with a couple misclassified points. The third case that I want to mention today is the case where not only do you have these points that are not necessarily linearly separable, but you also could have other points that need to be classified. Therefore, what we aim to do, in some sense, is to separate this into three or more regions. Obviously, this would be an example of our nonlinear separability case, but what if the number of groups inside of a classifier is not equal to 2? Right? So there's more sophisticated methods out there for SVMs that can solve this problem, but we're going to give you the more analogous way that is similar to pairwise comparison tests. So the first method that I want to introduce to you is the one versus rest approach. Some people will abbreviate this just by 1v all. So what we're going to do is we're going to suppose that the number of unique values for y is equal to g, where g, of course, needs to be greater than or equal to 2. So let's just draw a picture to sort of get an idea of what we're going to be doing. So we're going to have these circles, we're going to have these triangles, and then we're going to have our squares. So what we're going to do is have, our classifiers, for example, A1, A2, down to AG, and these are all going to be subsets of y. And then we're going to have a binary classification algorithm, SVM. So the first is going to be A1 versus everyone else. So the complement of A1. And then we're going to have A2 versus everyone else, and then A3 versus everyone else. Right? And that's going to continue the process for all of them, all the way down to A3 is equal to G. Right? And then we're going to have a result associated to that. Right? So in this case, notice that we have three categories: circle, triangle, and square. So what we're going to be doing is we're going to do circle versus everyone else. So circle versus everyone else obviously is going to be separable, and then you're going to drop a point, and then you're going to classify. So for example, if this is your decision boundary in this particular picture, and let's assume that we drop this point here, then that point would be classified as circle because it's on the positive side of the positive boundary, if, for example, this is the positive boundary. So if that is our outcome, then we're going to classify that as A1, our first category. And then we're going to repeat the process. So for example, let's assume that we're focused on triangle. So if we're focused on triangle, that means it's going to be triangle against everyone else. That's going to be a linearly separable problem because now square and circle are the same exact points. And here's going to be your decision boundary. And let's assume that our same point is over here again. I forgot where I put it. But if that's where our point is, obviously notice that that's on the opposite side of the decision boundary from what we're trying to classify with respect to. Therefore, that's going to be A2 complement. And we're just going to repeat this process for all categories. So let's assume that A3 complement is 1, and then A4 complement is 4, with the possible example that G is equal to 4, which is not necessarily this picture, but we can throw in some stars just to make sure that that is indeed the case. So once we have this particular setup, how are we going to classify? That's the question. So how to classify. Right? What we're going to do is we're going to be doing plus or minus 1 voting. Right? So let's assume that our binary SVM outcome are as follows: A1, A2 complement, A3 complement, and A4. All right? So A1, A2, A3, A4. We're going to be putting a +1 if you're accounted for in this outcome. And we're going to be doing a -1 if you're not accounted for in this outcome. So obviously A1 and A1 match, so we're going to get a +1. Since we're in A1, we're not going to be in its complement, therefore that's going to be -1, -1, and -1. If you're not in A2, that means you could be in A1, A3, or A4. If you're not in A3, that means you could be in 1, 2, or 4. And you're in A4, that means you're not in A3, A2, or A1, potentially. So then what we're going to do is we're going to total them up. So that's going to be 1 + 1 + 1 - 1. That's going to be equal to 3 - 1, which is going to be 2. And then we're going to have 1 - 3 - 2, then -2, then 2. Right? So in some sense, these are our binary ± 1 votes. So this is going to be a tie. So this is going to be a tie for A1 and A4. So in some sense, it's a 50-50 split. So we can either classify it as 1 or 4 or pick one at random. The second method that you could do for this is called 1 versus 1. So for 1 versus 1, how is this going to work? So for 1v1, we're still going to be doing a binary classification algorithm, but instead of focusing on 1 and its complement, we're just going to be focusing on 1 and a particular other. And we're going to be abbreviating this by 1v1. So in this case, we're going to have a 1v2, a 1v3, a 1v4, a 2v1, a 2v2, a 2v3, and 2v4. But keep in mind, some of these things are going to repeat, so we need not consider the different orders of, for example, 1 and 2. So 2v1 is the same as 1v2, so we need to consider it. So 1, 2, 1, 3, 1, 4. We also have 2, 3, and 2, 4, and we also have 3 versus 4. So in this case, we're going to have a total of G choose 2 binary classification algorithms. And again, once you have each of them, either you're going to be voting for 1 or 2, 1 or 3, 1 or 4, and so on. And then we can do, for example, plus or minus voting again. And then we can take a majority vote. And that gives the classification of a particular point. Of course, these are not true multi-class SVMs, but they are in some sense binary ways to get around it. We'll talk about more advanced SVMs later, where it actually truly is multi-class. But overall, these are the basics that you definitely need to know when it comes to support vector machines and how to use them. Hope you enjoyed this video, and I'll see you in the next one. Take care.